Hi all, welcome to part 14 of the video lecture on counters. So here in part 14 and 15 we will see some special type of counter. So they are basically they are registers only, but some kind of counting they are doing. So we can call them as counter also. Even counter itself is a variation of register only, right? So we will see that. So first one is called ring counter and another one is something like a twisted ring counter or Johnson counter. So that we will discuss in the next video. Okay. So let me introduce you all the context, right, where it is needed. So it's something like just read this line. Timing signals that control the sequence of operations in any digital system can be generated by a shift register or by a counter with a decoder. Okay, so I will try to explain what this line is trying to say. In any digital system, maybe computer or some other digital system, there will be a sequence of activities, right? So each activity will be controlled by a particular device, some kind of logic device. So it may be anything like maybe the arithmetic addition or some shift operation or some comparison operation, whatever it is, okay, or something different that the system is supposed to do. So there will be a sequence, right? So first I want to activate this particular device so that it will do what it is supposed to do. So by default we assume that sequential execution of any computer program, right, or any computer task. Sometimes the execution may be parallel also, that is a different thing, so that more than one thing is to be done at the same time, so accordingly you have to enable them. So right now so let's assume that sequential execution. So my requirement is like first this particular logic device which is doing some particular set of task or a subtask is to be activated. After that this is supposed to activate and then this is supposed to activate, like that. I just want a number of things to be done, okay, some 1 to n activities are to be done. So what is needed is like these are all like the enable inputs, right? So hope you remember this enable input. I mean, with any whether it is a decoder, encoder, adder or whatever it is, you can add something called an enable input with that, and whenever this enable line is giving a high value, so if it is active high, so whenever you are getting a high to that particular enable, that particular device will be activated and it will do the task it is supposed to do. Okay, so that is a basic idea, something like that. So who will enable these enable pins? Okay, so and that should be happen in a systematic way. So this is our requirement. For example, if you are executing an instruction, so there will be some systematic way, like the instruction will be fetched first, so the fetch unit is to be activated, then it is to be decoded, so then you will give a control to that decoder, so that decoder will work after that fetching. So you are not supposed to do the decoding before fetching, that is meaningless, right? Then execution right back, so like that. Okay, so that is the flow. Now who will enable these individual tasks? So that is a question. One way you can do is something which you are already familiar, the counter you can use. Okay, and you know what is basically a counter? So you are having a counter circuit and this counter is basically a register, right? Some which can do this counting. So let me assume so okay, so this is a general idea, and this this general figure we will see after seeing a special case, so that you can generalize everything. Okay, so in the next slide let me take a special case where I just want I'm just having 4 tasks to be done. Okay, 4 logic devices are there and I want to activate them, so that is my task. So for activating 4 devices, what I can do is I can just use a 2-bit counter. Okay, let me call it as a 2-bit counter. 2-bit counter, and for the 2-bit counter, what is the input? Input is something like a clock, right? And how this counter is being implemented, it may be implemented in a asynchronous way or in a synchronous way. Those things I am not highlighting here. So assume it as a black box, you don't know what is happening inside, and what is happening inside we already explored, right? It can be asynchronous, so that to the first flip-flop you will apply the clock, so that others will take the output from the previous one. It can be synchronous counter also, so that all of them are triggered simultaneously. Anyway, you will apply this clock, and some set of D flip-flop or T flip-flop, JK flip-flop, those things we will be using and mostly we will use the T flip flop, right? Because toggling is a basic activity that is happening in any counting, and they will be triggered based on the input, and that configuration, everything you know. So something like that is already there inside the circuit. So as it is a 2-bit counter, it will give 2 bits as a output, and you know these 2 bits are like it can be at any time, it can be 0 0, or it can be 0 1, or it can be 1 0, or it can be 1 1. Okay, so like that some 2-bit combination you are getting the output. Now what you are doing is you will be using something called as a decoder circuit, and decoder circuit is something we already discussed in the combinator circuit design and that time. So what kind of decoder you are going to use? So decoder and encoder, hope you remember, given any information, encoder will give the coded form. Now this output of the counter is basically the coded form, right? Because it is giving you something like a 0 0 or 0 1 or 1 0 1 1. So these codes are what the counter is outputting, right? And this code I am applying to the decoder, so that what kind of decoder I need? Some 2-bit code is coming, and you will take it as the input to the decoder, right? And the decoder will decode this 2-bit into one of the 4 output. I mean, using 2-bit 4 combinations are possible, right? So the decoder will be having 4 output line, right? And at any time, if that 0 0 is coming, this output line, first output line will be activated. If it is counter is telling 0 1, this will be activated. Counter is telling 1 0, this will be activated, like that. Now each of this output line you can connect with a particular device which is to be enabled, right, at the enable input, something like that. Okay, so here also, and you will do that with this one, and here also you will do the same. Fine. See, this is a basic thing. Okay, so now you can generalize it, this concept, like so in the previous diagram I taken some n devices, so that what kind of counter you need? You need is, what you needed is an n-bit counter, right? N-bit counter means, so n-bit counter, can you tell me 2-bit counter is basically what? 2-bit counter is otherwise called, it can count some 4 different information. So it is modulo 4 counter, right? Modulo 4 or simply mod 4 counter is what we are having, and here it will be something like a mod 2 power n counter, because using n bit it can go for 2 power n combination. Yeah, now there is something tricky here, because you know, here you don't want 2 power n values, right? Because you just want to enable n devices only. So for for 2 power n devices, if you want to enable 2 power n counting sequence you want, and that time you will be using a n bit counter. Now the question is, you just want to enable only n devices. Okay, so 2 power n and n, how they are related? This is actually logarithm of this. Okay, so if somebody is having doubt, suppose I want to enable 8 devices, right? 8 devices. So that I'll be using, so let me take this. So here I am removing this. Here I made a mistake. I will tell you what is that. Yeah. So see here, you used a mod 4 counter for enabling 4 devices. So here I have a device 1, 2, 3, 4 devices. Okay, so let me write like this. Number of devices I am having is 4 in this example. So that the type of counter used is actually 2-bit counter, right? 2-bit counter. And this 2-bit counter is otherwise called what is 2-bit counter is otherwise called a mod 4 counter, and that you know. Okay, and the what about the decoder specification? Okay, so the decoder you used is a 2/4 decoder. Okay, 2/4 decoder. Fine. Now tell me, if there are 8 devices to be enabled, what you will be using? So you will be using a 3-bit counter, because you know, using 3 bits you can generate the counting sequence like 0 0 0 to 1 1 1. I mean 1 1 1. That means 8 different combinations are possible, and each will be given to a 3 to 8 decoder. So now decoder will be something like a 3/8 decoder. So that 3 bits counting sequence will be given as input to the decoder, and that will decode the 3-bit to 8 combination. So accordingly, one of the device will be enabled. Okay, so and that will happen in a systematic way because counting is happening sequentially, right? Starting from an initial value, say 0 0, then 0 1, like that. So accordingly, the device will be enabled. Now you have 16 devices, you will be using a 4-bit counter, right? Counter. And here you will be using 4-bit sequencer generated 4/16 decoder, and that will do this for you. Yeah, that about it. Now can you tell me something like if there are 1024 devices, 1024, some 10 bits are needed, so you will be using a 10-bit counter. How I am getting, because using 10 bits I can have a 2 power 10 combination, and that is 1024. Using 4-bit I can have a 2 power 4 combination, that is 16. 3-bit I can have a 2 power 3 combination, that is 8. Okay, so that here you will use 10 by 1024 decoder. So that is a way. Now can you tell me what about a value of n here? Okay, what about, so how these numbers are related? 1024 and 10, 16 and 4. You know, it is something like here you need some k bit counter, right? K bit counter, and I don't know this value of k, and this k bit counter, if I am using this k by n decoder, I will be using. Now the question is, what is this k? Okay, so can you tell me how this n and k related? Here you know, so that I am writing here, so just listen. So here you know, from here to here the relation is something like this 2 power 10 is 1024, right? Similarly, from here to here it is 2 power 4. From here to here it is this 3 you are taking, 2 power 3, like that. Then from here to here the relation will be this 2 power k will be your n, right? 2 power k is equal to n. Then can you tell me what is your k? K is logarithm of n to the base 2. Hope you remember this in your mathematics class, or let me tell you how we are getting. You are taking logarithm on both sides of this particular equation, and you know, if x is equal to y, right, then log x equal to log y. Hope you remember this. You might proved it in your smaller mathematical classes, right? So if you take logarithm on both sides of any equation, the value remains same. Similarly, here we know that 2 power k equal to n, so you can take logarithm on both sides, that is log 2 power k is equal to log n. Right. Now for logarithm you need a base, and base, what I am doing is I am taking the base as k. That I will tell you why I taken the base as k. There is a reason for that. You will understand now. Because at this point, can you tell me what is log 2 power k? Log 2 power k. Log a power n. Log a power n is always n log a. Hope you remember this formula again. For any base, whatever be base of the logarithm, whatever be base of the logarithm, log a power n, that you can write as n log a. Same thing you can apply here also, so that you can write this from this point you can write like k logarithm of 2. Sorry, I have to take logarithm to the base 2 on both sides, right? I will tell you why it is. You will understand now. Okay, so at this point I find like what I explained is wrong. Now I am correcting. Okay. Yeah, I am taking logarithm on both sides, and I need a base for it. What I am saying is take base as 2. We will see that. So here if you write like this, whatever be the base, this 2 power k you can write as k log 2, and the base is 2 is equal to log n to the base 2. Right, like that you are getting. Now can you tell me what is this log 2 to the base 2? So that is a question. What is this log 2 to the base 2? We have again formulation, log x to the base x is always 1 in logarithm. So whatever be the number you want to take logarithm, if the number and the base of logarithm, if both are same, then that whole thing vanishes to 1. So same way you can take it as 1. Okay, so what you are getting from this point is k is equal to log n to the base 2. So this is what I am trying to say. So actually you need is a k bit counter, and that is nothing but a log n to the base 2 bit counter you are using actually, because we don't want a variable there like k and all. We just want to express this k as a function of n, because you know log so can you tell me now how this 1024 is related to 10? It is actually log 1024 to the base 2 is this 10. Why it is so? Because log 1024 is 1024 you can write as 2 power 10, right, to the base 2. and that is equal to, by logarithm property, 10 log 2 to the base 2. Now you know this log 2 to the base 2 is 1, so that this is nothing but 10. Okay, so that is how these two things are related. Similarly here it is log n to the base 2 bit counter we are using. So at this point you can write it like what we are having is a log n to the base 2 by n decoder we are using. Okay, so this is what I want to generalize. So here I made a mistake. I need a n different counting sequence. So what I need is not n bit counter. What I need is a log n to the base 2, this many bit counter, so that this log n to the base 2 counter can generate. Okay, so this can generate 2 raised to log n to the base 2 counts, starting from log n to the base 2 that many zeros to log n to the base 2 that many ones. So that is this many counting sequence. And what is this value again? This is again 2 raised to log. Okay, so here some logarithm came, but you can, by example also you can understand this. I am trying to generalize things. 2 raised to log n to the base 2 is actually, this is equivalent to n raised to log 2 to the base 2. This is again from logarithm property, like a raised to log b to the base c is equal to, without changing the base you can exchange this a and b, the value remains same. So for these are all basic logarithm formulas, and we have proofs, everything which you might studied in your smaller classes. Okay, I'm just applying them. Without changing the base a and b, you can exchange, the value of the logarithm remains same. So that is what I done. Without changing this 2, I exchange this n and 2, so that I am getting something like this. And this is nothing but n log 2 to the base 2. You know, you already know, I explained, like log x to the base x is 1. So this is n. So that is nothing but n counts are being generated. So this n count, when generated by this one, will be fed into a counter, decoder. So what kind of a decoder I will be using? N by, so n counts are being generated, right? Log n to the base 2, that many bits. So using that many bit, sorry, again making mistake. So that many counting sequences are generated, but each counting sequence is log n to the base 2. So I am having log n to the base 2 bits as input to the decoder. So this decoder specification is now important. So what we are having is log n to the base 2 bits by n. Decoder is what we are having. I am slightly, I don't know whether you followed everything. Okay, but still you take some small example and you try to generalize if you are not comfortable with the logarithm aspects. Anyway, we don't need this much detail. I was trying to explain this concept. So the concept is like, I just want to enable some n devices. Okay, to enable some n devices, one way to enable n devices is use a counter, synchronous or asynchronous counter, which is implemented using any kind of flip-flop, like what we already studied, and a decoder, right? So counter plus decoder can generate timing signals. So typically this output signals is what we call as timing signal. They are generated in a timely fashion to enable each and every devices. Okay, so something like that. So this is what is written, the timing signals, right? So here we have that n timing signals, right, that control the sequence of operations in a digital system. So all together this n devices together make the digital system, right, can be generated by, so shift register implementation I will tell you. So that is what we are going to see, or by a counter with a decoder. This counter with a decoder combination is what I explained. Counter and a decoder combination can generate timing signals in any digital system. So this is a conclusion we have. digital system, and I tried to explain that in a little bit detailed way, because so if you understand, it's very good, otherwise leave it, just take this conclusion. Okay, so let me explain once again for those who are following correctly. So I have n devices, right? To enable n devices, I need n timing signal, and that should be generated in a systematic way. Like first this should be activated so that this device will be active. It may be active low or high, whatever it is. Then this, like that. So accordingly, the counting sequence should come, right? And counter, when you initialize with some value like a 0, all 0, log and bit that many 0, it will give a 0 0 0 0 0 1, like that. So each so it's giving a code, right? Some kind of n bit code it is giving, and that you are applying to a decoder, so that this decoder will take this coded information and it will decode it to one of the outputs. Here n outputs are here, that many out at any time only one will be activated. Hope you remember how this decoder is working. Okay, so for example, if all bits are something like a 0, suppose the very first thing, only this will be enabled, right? All others will be disabled. Okay, so that this will be 1 and all others will be 0. Okay, so for this particular input, okay, I think we don't need it. You got it, right? So similarly, another coded sequence, when it is coming, and it will decode, and one of the n devices will be activated, the others will be deactivated, and that will happen in a systematic way. How it is happening in a systematic way? Because of the counter on the background that is generating the counting sequence in a systematic way. And for n devices to be activated, you need a n output signal from the decoder. So the decoder specification is like a something by n, like that. Okay, so n output. And for generating say 16 combination 4 input, right? So 8 combination 3 input, like that. For n output, log into the base 2 input code is needed, and that is being generated by a log into the base 2 counter, right? And which is nothing but log into the base 2 counter means it can generate log into the base 2 that many bits, like all zeros to log into the base 2 number of zeros to log into the base 2 number of ones. So that many counting sequence it will generate, and if you count it, it is something like a, using 4 bit 2 power 4 combination, like that. Here using log into the base 2 bits, 2 power log into the base 2 counts are there, and this 2 power log into the base 2 is nothing but n. That is what I explained here. So from this logarithm property. Okay, this may be slightly confusing, but anyway, this is the idea. Okay, it's always better to understand things in the right way. Okay, so that about it. Hope you understand. And this example also understand. Now let me introduce a different concept which can do the same thing for you. So now this you might feel like some counter is needed, log into the base to that many bits counter, and another decoder is needed. Now can I do it in a different way? So ultimately what I need is some n signals are coming out from the circuit, and that is enabling one after another device in a systematic way. First this is enabled so that this is 1 and all other things are 0. So something like this. The output of the circuit is something like if this is 1, all those things should be 0. Okay, this is one possible output I want. After that, after the next clock cycle, so for everyone we have this clock, right? That concept is there. This is 0 and this is 1, all others are 0, like that. So that this alone will be enabled, and then after the third one will be enabled. So something like that is what is needed for me. So I am trying to come up with a different design for that, and it's very easy. You can just implement it using a shift register. Instead of using a counter and decoder, the same thing you can implement using a shift register. So let me tell you how it can be implemented using a shift register. So what I am trying to do is, okay, let me tell you the design specification. I don't know what to be used inside. I am telling you the answer, it is shift register. So the thing is that some clock I am applying, always clock will be there, and at every clock tick, like a rising edge of the clock, I want some n output signal from the device. And out of this n output to signal, this output should give me a pattern, something like initially this is activated so that all others are deactivated. Then I don't want to activate this, then this is to be activated, all others are deactivated. Then I want this to be activated and all others are deactivated. Something like that is what is needed for me. So what I am using is a n bit shift register. So this I am trying to instead of that counter and decoder combination, I am trying to use a n bit shift register, right? Just a n bit shift register. And shift register is basically created using this D flip flop. Okay, so that there are so can I draw it in a vertical way? n D flip-flops are there, right? N D flip-flops are there. And you know how these D flip-flops are configured. So all of them are collectively activated by this common clock because they are registers, right? And I hope you know about how things are working. Okay, so this is our clock, and I applied clock to everyone. So all are D flip-flop, and you know for D flip-flop, let me write like this is the D input. Okay. Okay, let me use a different color because typically we draw the diagram in a horizontal way. Now I am drawing it in a vertical way, so that is why I am marking this D and all like this. This is a D input of this is a D input of this, etc. This is a D input of this, right? And the output, that is the Q output, right? Q output, if you want. Okay, that is there. Okay, the diagram is small, so this Q output, and this Q output is actually this. I am taking the Q output like this, and also hope you remember this Q output will be connected here, and there is one more. Okay, and hope you remember, and each of this output should be given as input to the next D flip flop, then only that shift, this is how the shift register is working, right? Hope you remember. In the output of the each D flip flop we will connect as input to the next I mean this is the first one. So some input. So you have to apply some input to this. Okay, so this is something like a serial in parallel out register. Okay, so some input is coming. So first you have to understand what is the serial in parallel output. These things I explained previously. So watch the register video and come to this. Then only you will follow this. Some kind of serial in parallel register is what I am using. Okay, and the serial input is coming like this, right? And it is shifting like this, and at any point I am taking like that, or I am okay, I am initializing it with the 0 0 0, and then I am trying to have the sequence. And now you got it like how to have the sequence. One way is you can just have this 1 0 0 0 something like this. So the output is like, so this n bit output, it's coming like this, right? So this vertical diagram might be confusing for you. Same thing I am drawing in the horizontal manner also. So what I was trying to use is I am using this D flip flop I am having. Okay, let's see that implementation using 4D flip flop. Okay, 4D flip flop, because 4 timing sequences are what is needed for me. And you know for D flip flop, this is a D input. Okay, and there is a Q output. Okay, so now it is clear. So that thing I have vertically drawn here. So that's all. And you know the output of every flip flop I will be connecting to the D input of the next one, like that. So that's all. Now what I am doing is this output I am taking as the I mean in a parallel way also, so that the devices can be activated, and each of this output I will be connecting to a particular device. Okay, so what is needed is, so this is connected to say device 1, and this is my device 2, device 3, etc., some device n. So in this case this is connected to device 1, device 2, device 3, device 4. So for enabling 4 different device I can have this kind of a circuit. In general, for enabling n different device, use an n bit shift register like I shown before, and so that it will have a dn d1 to dn, that many outputs will be there. Now what could be, so this clock also I am applying like this to all the flip flops. It's a very simple circuit, right? Simply the shift register I am using, serial in parallel out kind of thing, or some way you can use parallel in parallel out register. So somehow you have to initialize the flip flop in such a way that the initial value should be 1 0 0 0, so that only device 1 is activated now. And after initializing it, you can simply apply the clock so that this shifting will happen. And you know how this shift register works. It's a very easy thing. So the output of the shift register, don't know whether yeah, those things are drawn in a different way in your textbook. Anyway, now you are getting it. The output of the shift register, let me draw it like a device 1 Q1, device 2 Q2, device D input 3 Q3, D input 4 and Q4, and this D Q4 Q, those here also I given this same D. Let me use small d for the device. Okay, this is the capital D, and that D flip flop input, that is what I mean. So here devices I am naming like a small d. Okay, you should not be confused between this D is for D input of the flip flop, and this is for the device which is activated after this. So if you are analyzing the output, that is Q1 Q2, Q3 and Q4, you will see that initially it is something like 1 0 0 0. After applying one clock pulse, right? So the clock is being applied like this will change it to, once I trap this 1 here and 0 0, initialize like that, I'm just not giving any other input, okay? Or you trap this particular input in a serial manner or parallel manner, that you can choose anyway. But after this, just remove the input completely from that, so that after every clock cycle, now I want to do one more thing, because this timing signal is to be produced in a systematic way. This last output, so this is a further, in the normal shift register, the type of adjustment I am making is the last output of the shift register I am connecting here. I didn't done that crossing, so because they are not touching each other, okay? So think that. So output of the last D flip flop I connected back to the input, so it look like a rotating kind of thing, right? Shift and rotation, so some kind of a rotation device. So this is how I am, and I initialize like that, so that after applying on clock pulse, what could be the output? The output will be like this last 0 will come in the first flip flop, so that this 1 will shift here, this 0 will shift here, and this 0 will shift here, and this 0 will come back, because some kind of rotation is happening, right? Then in the next clock cycle, it will be like a 0. This 0 shifted here, this 1 shifted here, this 0 shifted here, and this 0 is coming back. And then again 0 0 0 1, and finally again back to this. So the sequence is something like again, so after applying one more clock, you will get this. So 1 2 3 4 different states are there for this particular configuration. So 4 states are there for the shift register. So it will go, if you are drawing the state diagram, this is one of the state, and from here it will go to 0 1 0 0, and from this state it will go to 0 0 1 0, and from here it will go to 0 0 0 1, and back to this. So like that it will rotate, and it will generate the counting sequence in a very nice way. First device 1 activated, then device 2, then device 3, then device 4, again device 1, like that. So typically digital circuits, they are working like that. Some such set of people will be there, set of in the sub devices will be there, and they have to be executed in a systematic way, one after another. So that is a very important application of this something like this shift register and counter. And anyway, if you are still confused on the application context, you will understand it clearly when you study that computer organization subject, and that time you will see that CPU design, and then you will appreciate this, how this timing signal is correctly generated and what is relevance of this topic, okay? So if I have a shift register that can do the shifting, and it's doing it in a ring way, right? The last output I'm connecting in a circular way back to the first one. So this is what I can call as a ring counter, okay? So this is connecting like a ring. The basic ring counter is basically a shift register only, serial input. Somehow you have to initialize it with the 1 0 0, that you can initialize parallelly or serially. So it can be a serial in or a parallel in register. Output you are typically taking in a parallel way, okay? So the implementation you can do in any ways. So basically a shift register made out of set of D flip flops connected in a cascaded way, and the difference is the last output I am connecting to the first input, okay? So if I am having this kind of a configuration, I can call it as a ring counter. So this is a 4-bit ring counter, right? So 4-bit ring counter can go through 4 different states. So there are 4 states, that's all. Yeah, something like this. So similarly for generating n different timing signal, n such D flip flops are needed. So now let me give you a small analysis. Like the requirement is like I just need n timing signals, n different timing signals I want to generate. So one thing I can do is, hope you remember what we discussed first is use a counter. What kind of a counter? N bit counter, not n bit counter. The counter is supposed to give n counting sequence. So I can call it as a mod n counter, okay? Mod n counter. Mod n counter, or mod n counter is nothing but log n to the base 2 bit counter, okay? So both these things are same. So this is a very important concept actually. Plus, right, so this counter is going to generate log into the base 2 bits, and I will take those log into the base 2 bits and I will apply it to a log into the base 2 by n decoder. Okay, so this is one way of achieving all together. This is one way of achieving or generating n timing signal. Now the second approach I am having is use n bit ring counter. And you know the n bit ring counter is nothing but the one made out of n flip flops. So here if I am looking at log into the base 2 bits counter, so this one is in need of just n flip flops, nothing more. But here how many flip flops are needed? Number of flip flop needed is less, right? Because log into the base 2 bit only I have to count, so that many flip flops will be used, right? Log into the base 2 flip flops will be used. Now what about the decoder? Okay, so decoder, it is taking I don't know whether you remember the implementation or not. Decoder typically some n AND gates will be there, the implementation of decoder. Just like if it is a 4/16 decoder, 4 inputs will come, and accordingly like input like I0, I1, I2, I3, so that the first output of this decoder is nothing but I0 you are taking as it is, and the other bits you are taking the complement, and you will be using a AND gate, right, for implementing this on the background. So it's already taken time. So if I am explaining that AND gate specification also, it will take time. So I'm not explaining that at this point. So you just see how that decoder is being implemented. I will just tell you the count, and to understand it you can refer our previous videos on decoder. Okay. So those who remember it, let me tell you. So what I need is for a log into the base 2 bit counting, log into the base 2, that many flip flops are needed, plus I need n AND gates. And I need n AND gates. And what kind of AND gates? Each AND gate is log into the base 2 bits. So like that. Okay, anyway here I just need n flip flop only. Here the number of flip flop needed is less, like log into the base 2, but the problem is specification of each flip flop. Yeah, that is fine. When it comes to the decoder's implementation, some log into the n bit to the base 2, log into the base 2 bits, that many input supporting AND gates I need, and that also n different AND gates. So I'm not supposed to use 2-bit AND gate. I have to use an AND gate which can take log into the base 2, that many bits as input. Okay, and such n AND gates are also needed. If you are implementing it using 2-bit AND gate, too many numbers will be in need. Okay, so that makes it a little complex. So this second design is always preferred over the first one, because just using n flip flop I can achieve it. If you are looking at first one, log into the base 2 flip flops are needed. Number of flip flop wise it is less, but the AND gate alone n number are needed, and that also log into the base 2 bit input AND gate. So all together complexity wise the second implementation will be better, and that is being achieved by ring counters. Now you got the idea fully. Now you can just go through it. I explained everything. So the timing signals that control the sequence of operation in a digital system can be generated by a shift register. So what kind of a shift register? So this is our ring counter, is what we've seen. So it's basically a shift register only, and to which the last output I am connecting to the first input. Okay, or by using a counter with a decoder. So this is another way of implementing the same. Okay, counter and decoder. Yeah, so a ring counter is a circular shift register. So this is what I was trying to say. It's basically a circular shift register with only one flip flop being set at any time. So at any time only one flip flop is being set, right? Others are 0. So 1 0 0 0 or 0 1 0 0, like that. All others are cleared. The single bit is shifted from one flip flop to the next one, producing timing signal in a systematic way using the clock pulse. So figure in the next slide shows a 4-bit shift register connected in a ring counter fashion. We will see that the initial value is something like, as it is 4 bit, same example I also taken 100, and requires by default at any time I should be able to preset and clear the circuit, because I just want to restart the timing signal. Accordingly I have to clear or reset something I have to do, right? So that kind of inputs are also needed for the flip flop. So single bit shifted write with every clock pulse and circulates back from T3 to T0. So T0 to T3 are the outputs, and the last output is actually T3, like a timing signal 3. I taken like a D3 something anyways, and it is connected back to T0. So each flip-flop is in the one state for every clock cycle. Like one flip-flop 1 is in one state initially, then after 4 clock cycle only it will come back to that initial state. Okay, similarly flip-flop 2, when it is in on state in the second clock cycle, then after 5th clock cycle, like that it will go. Okay, so this is the implementation. So the same circuits, basically these are all D flip-flop. I just drawn this in a very detailed way. This is a diagram given in the textbook. T flip-flop, the output are like Q0, Q1, Q2, Q3. Here they are writing like a timing signal T0, T1, T2, T3, and last one output I am connecting as the input to the first one. So, and the initial value is something like 100, so that it will go through the sequence like at any time. If you are looking at this T0, T1, T2, T3, you can see that it is like 100, then 0100, 0010, 0001, and back to this count, right? So that is what they said, like T3 to T0 back. Okay, so this kind of a so 4 different state it will go through. So the timing signal, if you are observing, initially it is T0 is 1, all others are T0 is high. If you are looking at T0 is high only during the first clock edge, and it's these things are by default assumed to be so where it is activated, it's getting activated in the negative edge. Okay, then they may assume a negative edge triggered a flip-flop. Okay, so from the negative edge to the next negative edge it's being activated, then from that point to the next negative edge, the second one T1 will be having a value high. Okay, so you got this timing diagram, right? So it's written clearly in the textbook, give the timing diagram also. So this timing diagram is equally important. So here it assumes something like a negative edge trigger. That is the way they are drawing the circuit. So accordingly they are written like a shift right signal, something like that. If you are applying the clock will be something like this. Okay, so that is what I understood from the figure. So this is something it taken from the textbook. And another way of implementing the same thing is something we already discussed. Use a 2-bit counter and count enable you can apply. So that time onwards it will give counting sequences like 0, 0, 0, 1, 1, 0, 1, 1, and these codes you are applying to a 2x4 decoder, and it will output T0 to T3. So here you don't have to do any ring kind of configuration, nothing. Simply use a 2-bit counter and 2x4 decoder. This also I generalized like log into the base 2 bit counter and to log into the base 2 by n decoder. Okay, so this is what I tried. So for an alternate design, the timing signal can be generated by a 2-bit counter. The explanation of that diagram, the decoder decodes the 4 states of the counter and generates the required sequence of timing signals. To generate 2 power n signal, yeah, this is what I was trying to signal. I taken in the reverse way, like n signal how many. So here they are taking in a more easy way, like output itself they taken like a 2 power n timing signal. So I hope you got the idea difference. I taken like a n timing signal I want. Accordingly I derived everything. Here they are taking like a 2 power n timing signal we want, so that 2 power n flip-flops are needed, and an n by 2 power n line decoder is used. Same thing what I explained is, instead of this I explained like n timing signal I want, so that here log n to the base 2, both are same. Okay, so that value only varies, and so that here it is like instead of n, that log n to the base 2 by n. This kind of a decoder I will be using. Okay, so I taken differently, they are taking like this, both are same. For example, 16 timing signal you want, so that you have to use a 16-bit shift register, right? And or another way is like a 4-bit binary counter and a 4/16 decoder. Okay, and in the first thing we need a 16 flip-flop, because what I am using is a 16-bit shift register. 16 D flip-flops are needed, and for the second one number of flip-flop is less, like 4 flip-flops only needed, and that generates 16 output, and those 16 output 4 bits you have to decode to 16 combinations. So for that 16 4 input AND gates are additionally needed. So this makes the circuit complex. Yeah, the last part, hope you remember hope you understand the analysis. Anyway, 2 designs are possible for generating timing signal in a systematic way in any given system, like timing signal 0, 1, 2, 3, like that. So one way is using a counter and a decoder circuit together, and another way is using shift register that is connected in a ring manner, what we call as a ring counter. Okay, now we will just see a slight variation of this ring counter called the Johnson counter in the next video. Yeah, thanks for watching. Hope you got an idea about it. This is a very important topic. You can expect this ring and Johnson counter, any one of them or both in your university exam for sure. Okay. So from fifth module, it's a definitely. So I don't think so. Someone will frame a question paper without this. Okay. It may happen. Sometimes they may ask us what is the difference. It can be anything. So after understanding Johnson counter also, you will get a clear idea of it. Okay. Thank you.